Sometimes we might want to approximate the binomial distribution by using the normal distribution, and that'll come up in later chapters. But to examine situations where you can use the normal rather than the binomial, let's illustrate that with the problem that's shown here. So we're told a wildlife biologist examines frogs for a genetic trait he believes may be linked to sensitivity to industrial toxins in the environment. Previous research shows that this trait is found in 1 of every 8 frogs. Okay, the 1 in every 8, we're really being told here the proportion of the frog population with this genetic trait, and 1 in every 8 really translates into 12.5% of this population. The researcher collects and examines 150 frogs, and those frogs will be examined and they will be determined whether or not they have the genetic trait. So they either have the trait or they don't have the trait, which kind of makes this a binomial anyway. And because we're doing a count, and it's also a binomial situation because we're given the sample size of 150, and we're told the proportion of frogs that have this genetic trait. Okay, so all that tells me I should be using the binomial distribution. And let's look at part A of the question. It says here, assuming the frequency of the trait is still the same, 1 in 8, determine the mean and standard deviation of the number of frogs. So those formulas are listed a few slides back, and I'll show you the answer on the next slide here now in a minute. And in part B of the question, we're asked to verify that you could use the normal model to approximate the distribution instead of having to use the binomial. So let's go to the next slide where I've got this worked out. So dealing with the binomial distribution, we know our sample size is 150 and the proportion of the population with the characteristic of interest is 0.125. I work out the mean. The formula is given as n times p. So what does that mean? I expect 18.75 of these 150 frogs to have this genetic trait. That's the expected value. That doesn't mean that that's always the value. And my standard deviation, when I plug in the values, works out to be 4.05. Okay, part B of the question, can we use the normal distribution instead of the binomial distribution? Well, you can, as long as the expected number of successes and failures are numbers that are at least equal to 10. So they're either equal to 10 or they're greater than 10. When I work this out, the expected number of frogs with the genetic trait is, of course, the mean of this distribution. So I expect 18.75. That is a number that's greater than 10. And at the same time, I expect that the number of these 150 frogs that don't have the genetic trait, which is a failure in this case, is 131.25. That's also a number greater than 10, so my two conditions here are met, and yes, I can use the normal distribution. Now, let's go back to part C and D of the problem. We're told that the researcher examines the 150 frogs, determines that 22 of them have the genetic trait, find the probability that 22 of the frogs have the genetic trait, and do that using both the binomial and the normal distribution. And then based on our answers to part C, we're then asked, does that probability prove that the genetic trait has become more common? Now, by the way, we expect 18.75 of these frogs to have the genetic trait. It turns out that 22 of them do have the genetic trait. 22, yes, is bigger than 18.75, but is it a whole lot bigger than 18.75? I guess that's the question. All right, let's flick back here now. So going to slide 52 here, I went into Minitab and got the probability that x would equal 22 using the binomial. And note now that I'm using equal to probability here. And the answer rolls out to be roughly 6.7%, which if I round up, that's roughly 7%. And I also found the answer using the normal distribution, plugging in the mean and standard deviation from the binomial distribution. And that gives me an answer that's fairly consistent with the binomial. It's a little bit higher, but if I round both of these numbers off, I'm going to get roughly 7%. Now, by the way, I've shown you right here how you might work this, the answer for the normal distribution, how you might work that out by hand. This formula was given in your notes on the normal distribution, and it's actually located on slide 17, but I didn't really show you how to work that out because generally we don't. We usually use software in order to get the answer. So I've worked it all out there. If you wanted to go through the trouble of working that out on your calculator, you should get that answer of 0.07138. But let's go to Minitab and see how that would work. All right. So into my Calc tab, probability distributions, I've got the normal and I've got the binomial. So if I go to the normal distribution, I can plug in my mean, and our mean was 18.75 with a standard deviation of 4.05. We're looking for equal to probability, so that's probability density. Input my constant. I want to know what's the probability x is equal to 22. Click OK, and there's the answer that you see in the notes. And just for completeness here, if I go in and do this using the binomial distribution, click the probability radio button. We had 150 frogs chosen, and we knew that 12.5% of them would have the genetic trait. What's the probability x is equal to 22? And there's my answer using the binomial. All right, let's go back to our note here for a moment. So both of these distributions give me an answer of approximately 7%. So I've said, okay, there's an approximately 7% chance that 22 of the 150 frogs have the genetic trait. And 7% is not a really high number, but at the same time, it's not a really small number. As we're going to see in later chapters that pop up, usually a small chance is something that's 5% or less, and 7% is not all that small. So really we would conclude that the genetic trait is not really becoming more common in this population. Also, if you take 22 out of 150, you're going to get 0.146. So 14.6% of our sampled frogs have the genetic trait. But we know that the total population, that of the total population, 12.5% of them has the genetic trait. Now 14.6 is not radically different from 12.5. We worked out the mean to be 18.75. Does that mean that every time I take 150 frogs, I'm going to get roughly 18 of them or 19 of them that will have the genetic trait? No, I'm not. You know, sometimes I'm going to have 20, sometimes I might have 25, sometimes I might only have 14 or whatever. But in this case right here, 22 is not radically different from 18.75. Now, if I had sampled 150 frogs and maybe, I don't know, 120 of them turned out to have the genetic trait, well, yeah, that would be pretty strong evidence that the genetic trait is increasing. But in this situation, we would say no, that it has not become more common.